So hi everyone. First of all, let me welcome you guys to the Unacademy JEE English. So this, as you know, is a brand new channel by Unacademy where everything is being taught to you completely in English. So this is a series that I host for class 12, 11 students, and the topic that we are discussing right now is rigid body motion. This is lecture number 7 of rigid body motion. Today we'll be talking about dynamics of pure rotation. So by the way, this is a recorded session, so I will not be able to interact with you guys. However, at Unacademy, we strive hard that your studies do not catch a break no matter what. That is why we are uploading this recorded video and hope this will help you in continuing your study of the topic that we are doing. Okay. So as I said, the topic today is dynamics of rotation. Now, before we get started with today's topic, let me introduce myself for those of you who might not know me yet. So my name is Rohit Dixit. I studied mechanical engineering from IIT Delhi, and for almost past 8 years, for more than 7 years, I've been teaching physics for the IIT JEE exam, and all this teaching so far had been offline. So offline, I have been associated with some of the topmost institutes in the JEE field, or at preparation field. Now, I myself, as a student who was an All India rank 447 and All India rank 192 in the two stages of the IIT JEE exam that I took, I also qualified at the NTSC stage 2 as a student, and I was in the top 1% in the NSCP, which you better know as the National Standard Examination for Physics, or the first stage of the Physics Olympiad. Now, I've already coached many students to top ranks in the IIT JEE exam, both mains and advanced offline, and now I hope to continue guiding you guys to top ranks on this online setup. So, moving forward, how can you guys make sure that your studies are going and you are getting those top ranks? This is how you can do it. You can get yourselves the Unacademy subscription. This subscription will give you benefits like live classes, where you get to interact with your educators on a regular basis. So this will ensure that your studies are going forward just like they would have in an offline setup. And here, these classrooms also contain live polls and leaderboards, which keep them highly interactive and fun. Now, you're also part of a test series, which helps you keep you on your toes, which helps you all aware all the time of your standing in the competition. And you have analysis sessions where your teachers will guide you about where you're lagging behind and how you can improve on those areas. And of course, the biggest benefit you have is a live doubt clearing session. So every fourth session in all the Unacademy Plus courses is a live doubt clearing session where you are. It is sure that after every three classes of teaching and practice, there are no doubts that you are left with. So make sure you are getting yourselves the Unacademy subscription and benefiting from all these wonderful features. And on top of all these features, Unacademy is also providing you the opportunity to study from the topmost educators from all across India, from the comfort and safety of your home. So make sure that you're getting this subscription, and again, studying from the best teachers all across India. Now, there are three courses which are ongoing on the Plus app of the Unacademy, which are being hosted by the JEE English team. So these are three courses that are of class 11 topics, mainly meant for class 2022 aspirants. However, all 2021 aspirants can also join these courses, and I can assure you that this will definitely help you master those subjects that are being taught under these courses. All right. So I myself am taking an advanced course on mechanics. Then there are two more courses which are being taken by Abhinav sir and Rahul Kaushik sir. All right. Now for 2022 aspirants or for 2021 aspirants, you have four more courses for class 12 topics, so including one that I'm taking, which is an advanced course on electromagnetism. So if you want to enroll in these courses, hurry up, get yourselves the Unacademy subscription. So how do you do that? Very simple. First, you'll need to install the Unacademy app. Once you have done that, then you will need to go to the plus section of the app, select your goal as IIT JEE and click on the get subscription button. Now, once you've done that, you will be redirected to the payment page where you will first of all realize that the fees of all these subscriptions has been kept very competitive. So a 24-month subscription comes to about 56,000, which is roughly 2,300 rupees per month, less than 100 rupees per day. Similarly, for 12 months, the subscription comes to about 200 rupees per month, which is roughly 100 rupees a day. So trust me, any reputed offline coaching institute would charge you anywhere between 4 times to 8 times this fees. So Unacademy is providing you the opportunity to get the same quality education from the same top educators at a very affordable, reasonable price, which will be made even more attractive if you use this code. So here you would see a column which says, do you have a code? This is where you can use this code RD Live and get an additional 10% off on all your subscription fees. Now, when you click on proceed to pay, you will also see that there is no cost EMI options available on 6 month and above subscription plans. So trust me, at these prices, at these costs, and at these options of payments, this Unacademy subscription is definitely worth having. Okay. So also don't forget to be a part of the Unacademy Combat. This is the most competitive gamified version of the IIT JEE battle. All right. So make sure you are attending this. You can compete live in this Unacademy Combat, and if you do well, you can win awards and prizes also. So the next Unacademy Combat is going to be hosted on the 22nd of October. You can enroll for it now using the code RDLive. All right. So moving forward, those of you who are following us on the JEE English channel of YouTube can connect with us on the Telegram app using this link. So you can become a part of the channel where you will receive all the notifications of all the lectures and amazing sessions that are being posted on the JEE English channel of YouTube. All right, so moving forward, and let's get started with today's topic, which is rigid body motion. And today we'll be talking about dynamics of pure rotation. Okay, so as I said, this is a recorded session, so I won't be able to respond to your chats. However, if there is any part that you do not follow, then you can always leave your doubts in the comment section, and I will try to answer either in the comment section only, or I will try and take up your doubts in the next live class that I take. All right. So as I said, in the last class, we started a discussion about torque and momentum, angular momentum. So we defined the term torque. We realized it was the ability of a force to produce a change in the state of rotation. And then we also realized that we also had another term, which was angular momentum, which is essentially a measure of the amount of rotational motion in any object. All right. So this was an analog of linear momentum from translation. This was an analog of force from translation. Now, so first, it is very important for us to identify how to write these terms before we can use them. So you already learned that torque can be written as the torque of a force about a point, torque of a force about a line. Similarly, we were talking about angular momentum. That also for a point mass, angular momentum is written always about a point, and that how you define this is r cross p. For any particle with having p momentum, the angular momentum about some point O is defined as r cross p, where r is the position vector of the particle with respect to O. Okay, so please remember that. So that was the definition for a single point mass. Then we look to find the expression for a body about any part or a collection of particles. So we realize that if you have any collection of particles or any body or any system of particles, and if you want to calculate the total angular momentum of this system of particles about any random point P. So how do we do that? So let's say here you have a point P, and if you wanted to calculate the total angular momentum of my system of particles about point P, then the way to go about that was that I realized that system of angular momentum of system of particles about P can be written as angular momentum of the CM about P, okay, plus the angular momentum of the system with respect to the CM. I hope you remember this from the derivation in the last class. Okay. Now, so how do you write this? This is very simple. CM is a point mass. So for CM, the angular momentum of the CM about P is very easy to write. This will just be R of CM with respect to P cross P of CM. Right. Now comes the tricky part. How do we write the angular momentum of this system with respect to CM? So let's take a look about that. So today we are going to, right now, we are going to in fact focus on this particular term, how to write this. Now we will only take a very specific case of this. Okay, so in general, you will know how to write this. So if I focus on this, let's see. In general, you know how to write this. In general, angular momentum of any system about any point would be nothing but summation of r of I with respect to c ith mass cross the linear momentum of ith particle with from the reference point of the CM. Okay, I hope you remember this. This is how you write the angular momentum about any point. Okay, so this is about any point. So if I'm writing about system about the CM, then I will write it like this. Okay. So how do I calculate the individual terms? Let's see. So what is this? Now, if I talk about a rigid body, for a rigid body, you will realize that the only motion that any point mass can do about the center of mass is pure rotation. I hope you guys agree that. Let's write that down. For rigid bodies, for rigid bodies, all masses can only rotate or perform, or let's say rotate about the CM. I hope you remember this from our discussion of properties of a rigid body. We discussed this already, that if you go into the reference frame of any point on the rigid body, then you will realize that every other point will start to perform pure rotation, right? So rotate about the CM. So I immediately know that all particles are performing pure rotation about the CM. So now I will know how to write their velocities with respect to the CM. So let's continue. The special case is that we are trying to calculate L of a body, of a rigid body, that is about its CM. So that is the special case that we are going to focus on about the CM. Okay, so let's draw ourselves a rigid body. So imagine that there is a rigid body and there is an axis passing through the CM. Okay, so let's draw ourselves an axis passing through the CM about which the pure rotation, let's say, is happening. Okay, so let's say that this is the axis about which the rotation is happening, and this is passing through the center of mass. Okay, and let's give this axis some name. Let's again call this A dash something. Now you will realize that how do we write the angular momentum? Angular momentum of rigid body. I will consider this rigid body to be made up of infinitely small point masses. So this, with respect to Cm, would have been nothing but summation of R of I with respect to Cm cross P of I with respect to Cm, which would have been mass of I times V of I with respect to Cm. Okay. Now you will also realize if I talk about the ith particle in the frame of the Cm. So let's say this is the ith particle. So when I'm trying to find this is R of I with respect to the Cm. And what will be the velocity? I hope you remember the velocity. Velocity would be V of I with respect to Cm would be nothing but omega cross R of I with respect to Cm. Right? Why? Because every point is in pure rotation about the Cm. Correct? Now you will realize when I do this R cross omega, what does that tell me? So omega vector obviously points out in this direction, right? So omega vector, let's say, is pointing in this direction. So everything is essentially rotating like this. Okay. Now R cross this is nothing but if I only want to write about the magnitude, you will realize if I talk about the magnitude, then this would be omega times R I with respect to Cm perpendicular. Okay. Because it will be omega RIC into sine of theta. Sine of theta would give you, if this is the theta, then this would have given you the perpendicular distance from the axis. Correct? I hope everybody can see that. That is what this is going to be. Now you also have to multiply the velocity vector, which is going like this, okay, which is obviously going to be perpendicular to this, and you have to cross multiply this with RIC. So what you will realize if you want to write the magnitude, if I only talk about the magnitude for now, it's because I don't want to show you the entire vector derivation, but I will just tell you slightly. So this is nothing but summation of mi, and you will have one RIC from here, one RIC from here. So R of I to C whole square, and this will be perpendicular whole square by the way, both the time, times omega. Now you will realize you can take omega common, and if you take omega common, what you have is this. Now this is nothing but I about the Cm. So what you will realize is that angular momentum of a rigid body about a Cm, about its Cm, okay, turns out it comes out to be ICM times omega vector. This is the equation that you want to use. Okay, this is what it boils down to. So remember this. This is a very important result. The angular momentum of any rigid body about cm would be always ICM, where ICM is the moment of inertia about the axis passing through the CM. So it is this in this case, in this particular case, it is this axis which has to pass through the CM times omega vector. So angular momentum points in the direction of the omega vector only. You will realize that I did not show you the vector derivation, but I hope the thing is clear. That you would have had one RIC here, you would have had one RIC into omega here. So this is what you are getting. This is what you're getting, and this is the final result. So very important. First, remember. Now we already know in case of pure rotation, the angular momentum of any rigid body about its CM, or rather about the axis of rotation passing through the CM. Okay, so this is about the axis of rotation passing through the CM. Okay, not only about the CM, because you have to take the component, and that is why you would have gotten that also. The another RIC perpendicular, that is how you would have gotten it. Okay, one RIC perpendicular you have gotten from here. Another, what you would have done it, that you have to calculate the angular momentum about this axis. So that would have been only this component of angular momentum could have been taken. So that would have given you another RI perpendicular with respect to C. Okay, that is how you are getting this. So remember, what is this? This is the angular momentum of the rigid body about the axis of rotation passing through C. Okay, I hope everybody is clear about that. Now, how about the angular momentum in pure rotation? Today, we will only talk about that. But about an axis of rotation which does not pass through the CM. So, special case number 2, angular momentum L about an axis of rotation not passing through the CM. So, that is what I want to find. Okay. Again, these derivations are not really necessary for you to understand and know. I just wanted to show you so that you know where and how every expression that you are going to use is coming from. So imagine again, we have a rigid body like this, okay, and let's say the CM lies somewhere here, CM lies somewhere here, and your axis of rotation is passing to this point, okay, and I want to calculate. So let's say this is a point P that I'm taking on the axis of rotation, okay, and I want to calculate the moment of inertia, the angular momentum about this axis. Okay, and here is my C. Now I will go back to the original formula. What did my original formula tell me? Original formula told me that angular momentum of rigid body about P, or about an axis passing through P essentially. What I'm doing is that. And I'm also assuming that if I am taking another axis which is lying parallel to this, why I'm doing that, I will just tell you now. So how do you calculate this term? First of all, this term is angular momentum of CM with respect to P plus you have angular momentum of CM, or the rigid body with respect to CM. Right? I hope you remember this. This was how you would find the angular momentum of any system of particles about any random point. Okay, so this expression. Now I already know how to calculate this. What is this? See, if I go into the reference frame of the CM, then what will happen is that I hope you remember that in the reference frame of CM, everything will start to perform pure rotation with the same omega about the CM. Okay, so in the CM now, what I will see is, so if this was rotating like this with some angular velocity omega vector, in the reference frame of the CM, you would have noticed that it is everything is rotating about this with the same omega. Okay, that is why I had drawn that parallel axis, because everything will rotate exactly with the same omega. Now, so the first term I already know. And how about the second term? Second term is nothing but R of m with respect to P cross angular or rather the linear momentum of Cm with respect to P, correct? Plus this I already have as ICM omega. All right. I hope you remember this. And now, not only I have to take this, but I will have to take the component about of this angular momentum along this axis. Okay, I hope you remember that because we are calculating angular momentums about axes, not points. Okay, so you will realize since there was pure rotation, so let's talk only about the magnitudes. Let's talk only about the magnitudes. So what will I see if I only talk about the magnitudes? So L of Cm with respect to P, what will I see is I will see there will be this R, and if I'm taking this, if I'm calculating this only, first of all, so what will be this? This will be mass, total mass times velocity of the CM. Velocity of the CM would be omega times R perpendicular, which is B. I talk about the perpendicular distance between the two axes as D, then this will be M omega D. Okay. Then I could have made the cross, and since I had to take the component along this, so I would have had to again multiply with the perpendicular distance only. So this is what this will become, this entire thing. The magnitude of this will become this. So I hope you realize where we are going with this. So the expression that we are going to get, the expression that finally we are going to get is going to be that angular momentum of a rigid body with about an axis passing through P would be md square omega vector plus ICM vector. Now, all you need to do is take that omega vector common and then you have ICM plus md square. Now, remember your parallel axis theorem. What does that tell you? That tells you the angular momentum about the axis passing through P. Okay, so this finally of a rigid body about an axis passing through P becomes I about an axis passing through P times omega. Again, a very, very interesting and important result. Okay, something that you should not only understand but must remember. Okay, I just wanted to show you the proofs of everything like that. Okay, so remember this result. The angular momentum of any body in pure rotation about any axis passing through any point P on the rigid body will be I about the axis passing through P times omega vector. Okay, so this is how you write the angular momentums in pure rotation. In pure rotation, all you need to do is use this expression. Okay, and you are sorted. Now, why don't we try a problem? So here you have been told that a rod of mass 2 kg and a length 3 meter is rotating about its end with an angular velocity of 3 radian per second. You have to find the angular momentum of the rod about the axis of rotation. Okay, I hope the problem is clear to everyone. What you are trying to find here. You're trying to find here the angular momentum of a rod which is rotating about its end. So something like that. Okay. So let me also draw a picture in case you want a little help for visualization. So imagine your rod is like this. Okay. Imagine this is your rod, has some mass m and some length l, where l is this, and this is rotating about an axis which is passing through the end like this, and with an angular velocity omega, which you know is 3. Okay. So this is the case. So find the angular momentum, and obviously angular momentum would always be directed in the direction of omega vector. Okay, for pure rotation, always remember that. For pure rotation, angular momentum is always directed in the direction of omega vector. So I'll maybe give you 1.5 minutes to answer this. If you followed the derivation, forget about if you followed the derivation. If you remember the formula, then this should be super easy, right? Let's see if you guys can write this quickly. Okay, I'll give you guys some time to figure this one out. Till the time, I will help myself with some water. Okay, so I hope most of you must have figured it out by now. It's very simple. All you needed to do was remember this one formula, that angular momentum of any rigid body about any axis passing through a point P is equal to the moment of inertia about the axis passing through P times omega vector. So here all you need to do is, this is the axis. Let's call this a dash. And what will be the angular momentum? Very easy, very simple to write. The angular momentum about a dash would be simply I a dash times omega vector. Okay. Now, if you're only talking about the magnitude, then let's forget about the vector sign, and all I can say is this is 1 by 3 ml square times omega, and if all I need to do is just substitute these values. So when I substitute these values, 1 by 3 into what was my m, m was 2, l was 2, and omega was 3. So m is 2 into l was 2, 2 square into omega was 3. So what you have is, you have your answer as 8. Okay, what are the units? Think about the units. What are the units going to be? So it's moment of inertia times omega. So moment of inertia was kg meter square, and omega units would be per second. Kg meter square over second. Okay. All right. I hope that was an easy one. So let's try one more. You have been told a particle of mass m is moving in a straight line, okay, parallel to the x-axis in the xy plane with a constant velocity v. Now find the angular momentum about the z-axis, and you also have to tell me, will that remain constant? So this is the question that has been asked in JEE Advanced also. Okay, so give it a try. So to help you visualize, let me just show you what the situation is. So the situation is something like this. So you have an x-axis, y-axis, and let's make a z-axis. Yes, you've been told that a particle of mass m is moving in a straight line parallel to x-axis. So let's make ourselves a straight line parallel to the x-axis in the xy plane. So let's say here the particle is moving with a constant velocity. Let's say it is at some random point here, and it is moving with a constant speed, or rather velocity v. Now you have to find the angular momentum about the z-axis. Okay, and if you also have to tell me if uh, angular momentum remains constant or not. Okay, so let's give you another one more minute to answer this. Okay, this is a relatively simple one. You should be able to answer this very quickly. Okay, so how do you calculate the angular momentum about an axis? Just remember that. So if you talk about the magnitude, if you want to talk about the magnitude, then the magnitude is going to be simply mvr perpendicular. Okay, where r perpendicular is the perpendicular distance from the axis of rotation. Okay, I hope you remember that. All right. Okay, 1 minute is almost up. So let's say it has this random position, and what is the r? So all I need to do is I need to draw an r which is already perpendicular to this axis of rotation. If I do that, then r cross v will always point in the direction of z only. Okay. If I chose any random arbitrary point from where I was drawing the r vector, then I would have had to take a component from this r. The entire r cross v, you realize, will point in the direction of z axis only, so I don't have to take any component. Okay, so let's say this is the r vector. Okay, this is where your v vector is going. All you need to do is calculate, I know, angular momentum for z axis would be r vector cross m times v vector. Okay, now obviously what you will realize is that the direction of r cross v, let's first figure out that. So r is going like this, okay? V is going like this. So the direction of r vector is going to be into the plane of the paper, okay? R cross v. And how about the magnitude? So if this is the angle theta, say this is the angle theta, then what you will realize is that this is nothing but m e r sine theta times minus k cap. Okay, direction I've already judged from judging the direction of r cross v. Okay. Now, how about r sine theta? Now you will realize that if you draw this, focus on this. So this is theta. If you focus on this triangle, if this is d, which is the perpendicular distance of the line of motion with the x-axis, then you realize r sine theta is always d for different thetas. As the particle moves, you realize even if the particle was here, then the theta obviously would have been this, theta dash would have been theta dash, then r sine theta would still be d. So I hope you realize that the answer that I'm getting, in fact, is very, very interesting. The answer is that this is mvp minus. So yes, it is constant. Not only did we find the angular momentum, we also realized that it is constant. It does not change. Okay, so that is an interesting result. So yes, it is constant. Okay. All right. Now let's move on towards the relation between torque and angular momentum. So this is again going to be very, very easy. So you already know how do you write your torque. So talk about any axis or any point. Let's say it doesn't matter about which I am taking. So any point P, I know would be R with respect to P cross F. Okay. Now all I need to do is remind you that F also, what is F? F can be written as dp by d. Okay, that's it. If I write that, then what do I have? I have tau about p equals r about p cross dp by d. Correct. Now I'm going to take another step and I'm going to tell you one thing very, very interesting. That I can write this as, so what is RP? RP is the position vector of the point of application of force. Okay. And the force at whatever point it is being applied, it will be changing the momentum of the particle. Okay, so by the way, this is for a single point mass. So let's add that. I'm only talking about for a single point mass. Okay, so for a single point mass, I'm trying to calculate the relation between tau and angular momentum. Okay, so this RP would be nothing but the position vector of the particle itself on which the F force would be acting. Right? So I am telling you that I can rewrite this as d by dt of r cross p. Now how do I do that? Let me show you a neat trick. So you realize if I wanted to calculate this, if I wanted to calculate only this part, focus on d by dt of r p cross p. So I can apply the chain rule and I can write this is dr by dt cross, okay, and plus rp cross dp over dt. Now you will realize how about this term? What is drp by dt? So rp was the position vector of the particle itself. drp by dt would have been v. V means the velocity. And velocity cross momentum. What will that be? That will be 0. Why? because momentum has V also. So it will have V cross V. V cross V is always zero. I hope you know that. That is why this term will turn down to zero. And that is why you can write this. So what you realize is that torque about P is equal to, now this is the angular momentum about P. So d by dt of angular momentum about P. Okay. So torque about any point for any particle would be equal to the rate of change of angular momentum about the same point. Now all you realize is that for a system of particles, again, for a system of particles, when you add all these torques again, so you will get the summation of all the torques would be equal to the d by dt of summation of all the angular momentums of all the particles of the system. So this is for a point mass, and you will realize for an entire system of particles also, this is the result that you would have gotten. Okay, that the rate of change of angular momentum for any body is equal to the net external torque applied. Okay, and you will realize that this is analogous to the second law of motion in a translation. Okay, so again, I am showing you some derivations which you might not be following, or you might be thinking, okay, why is showing so many derivations? Also, we don't need them. So yes, technically you don't need them. So if you don't like those derivations, don't worry. You can completely let go of those derivations. You don't really have to follow them. Follow these results. Everything that I'm putting in a box and marking with yellow. That is just to give you a slight more insight into things. In case somebody is interested. In case somebody wants to know how and why are these equations coming, or where these equations are coming from. Okay, because trust me, a lot of people know these equations, but they still make a lot of errors because they don't understand the derivations. And I will tell you cases where you will make errors. If you know the derivations, however, if at least you understand, you don't need to know the derivation, you just need to understand the derivation, then trust me, those errors won't be made. Okay. By the way, I hope everybody followed this. Okay. For every particle, for every constituent mass in the entire rigid body, I could have just wrote tau equals dl by dt equation for all the point masses, then added all of them together, and then this is the result that I would have gotten. Right? I hope you remember that. This is very similar to writing net f equals ma for translation. Okay, why? For translation, everybody had the same a. Okay, so similarly, in a pure rotation, you will realize in pure rotation, or rather, this expression is true even if there is no pure rotation, by the way. Okay, yes, I completely forgot about that. This is a general result, valid for all cases. So let's get that, valid for all kinds of motions. In fact, this will even be valid even if your bodies are non-rigid. See, what I'm trying to do here is, so if I had a system of particles, and on one torque acting was tau one, so all I would have written was tau one equals dl1 by dt. Okay, and then I would have written tau two equals dl2 by dt, and so on. I would have just written the torques on all the individual particles and then added them. If I add all such equations, then what I get is summation tau is summation of, I can write d by dt of summation li. Okay, I hope here we are using the distributive property, and this is nothing but system, the angular momentum of the system, d by dt of L of system. So this is valid for any system of particles. It doesn't necessarily have to be a rigid body. Doesn't necessarily have to be pure rotation. It can be any kind of body, any kind of motion. This is a general equation. The form that we will talk about next is a special case. So please remember that this is a general result. General result valid for all kinds of cases. This equation you can apply anywhere without thinking about it twice. However, next we will talk about a very special case. So before we do that, first we will talk about equilibrium first. Okay. So earlier you remember if any object was said to be in equilibrium if the net force acting on it was zero. Now we will stretch that definition to rotational equilibrium also. And now we will say that any body is said to be in equilibrium if it exhibits both equilibriums, one translatory equilibrium, another rotational equilibrium. Okay. So the condition for equilibrium would be that first the sum of all the external forces must be zero, and second is sum of all the torques due to these forces about any point must also be zero. Now, this is a very interesting result here. For rotational equilibrium, if a body is in rotational equilibrium, that is, if it is not rotating, you realize if it is not rotating, then it won't rotate about any point. Doesn't matter where you're observing it from. Okay, so here, if this pen is not rotating, then it is not rotating about any point. So, about any point, the torque of all the forces will be zero. So this is a new condition for equilibrium. Now, if only net force was zero, then we would have said the body is in translatory equilibrium. If only the net torque was zero, then we would have said the body is in rotatory equilibrium. If both of them are zero, then we would say that the body is in complete equilibrium. Okay, remember these. Okay. Next, let's talk about a couple of problems for equilibrium. You've been told a uniform rod of a 5 kg mass and 2 meter length is resting horizontally on two sharp edges as shown in the figure. Okay. You have to find the normal reaction on both the edges. Okay. So think about it. Think about it. What has been told to you that the body is resting. If the body is resting, then it means it is in both kind of equilibrium, both translatory and rotatory, right? So use the conditions for both translatory and rotatory equilibriums, and you can find the answers. So whenever you have such a problem, how do you approach it? You first make an FBD. Once you make the FBD, you write the conditions for equilibrium. The conditions for equilibrium was one, summation of all the forces would be zero. Second, summation of all torques about any point would be zero. That is how you would have approached this problem. Okay. Again, those of you who did not like the derivations, don't have to bother about it. You should focus from here on the application part. This is how you will apply it on in your questions. And this is how you will solve the questions. Find the normal reaction on both the edges. So how do we do that? Let's give you 1 minute to try this, maybe, or maybe 1.5 minutes. Okay. So I will wait for you guys. Again, have some more water, and then we will take a look at the solution. Okay. Think about what we have just discussed and try and get the answer. Again, I understand that a lot of people, a lot of you guys might be getting some headache with all the derivations. So what I'll do is in the next class, I will skip all the derivations, write down all the important results. Okay. So make sure if you do not like the part about the derivations, then you can just skip the derivation part of today's lecture and focus on the recap of that I will have in the next lecture, where I will just list all the important results that we derived so far. Okay. All right. I hope you guys were able to solve this. Okay. Yeah, it's almost been 2 minutes, so why don't I go ahead and solve this? And this is how you should have solved it. I don't know how you did, and I'll tell you how you should have. So first, you will make the FBD. So let's start the FBD right here only. One, I will have Mg acting on it. Then I will have two normal reactions. Let's call them N1 and N2. Okay, and let's say that from here I have N1 acting, two acting. Okay, so this is the FBD. Everybody agrees. This rod has only two contacts, right? With those two sharp edges. So both these contacts will give you an N, and then there will be an Mg. So first I can write equations for translatory equilibrium. So I will write for translatory equilibrium. What can I say? That the net sum of all the forces must be zero. Now all these forces are in y direction only. So can I say that N1 plus N2, N1 plus N2 must be equal to mg? Okay, I hope everybody agrees. Now for rotatory equilibrium, I know that the summation of torques about any point is zero. So which point to choose? Now you realize you could have chosen any point to find the torque equation. Okay, and you have two unknowns. You already have one equation. You only needed another equation to solve or find your unknowns. Okay, so let's give these points some names. So let's call this A, let's call this B, let's call this C, and let's call this D. Now you could have taken thoughts about any of these points A, B, C, D, or any other random point also and put that as zero. So what I personally like to do is take it about a point which makes my life slightly easier. So what I like to do is I will take the torques about point D. Why? That has two distinct advantages. One, I don't get any torque due to N2. Okay, and I already know the other values. Okay, so I'll immediately get the value of N1. Okay, so what are the torques about D? Okay, so also for rotatory equilibrium, okay, so we are taking torques about D. Let's see what do we have. Okay, so one, I will tell you an easy way of writing torques. So everywhere you don't have to write the cross product. So obviously the torque you will know is R perpendicular times F. Okay, that is how you write the magnitude. How about the direction? The direction is very, very easy to judge. So what you need to do is think of point D. About point D, N1. N1 is the force that is pushing the rod up, right? So it is pushing the rod up. So how is it trying to rotate it? It's trying to rotate it like this. So the torque, all you need to do is rotate your fingers in the direction of the rotation, and this thumb will point in the direction in which torque would be acting. Okay. So mg is trying to rotate it downward. So mg's torque would be coming out and n1's torque would be going in. So again, I am only going to write the directions with plus and minus. Why? That is the advantage, entire advantage of using angular quantities. So all the directions would be only in this, either that direction or this direction. I can denote them as plus and minus. I will denote this as plus. So mg stock would be positive and n1 stock would be negative. So what is the torque of mg? Mg has a perpendicular distance of 1 meter. N1 has a perpendicular distance of 1.5 meter. So mg stock would be plus 1 into mg and n1 stock would be minus 1.5 times n1 and this must be 0. Okay, now all I need to do is just substitute the values. If I substitute the values, m was 5 and L, okay, so L I don't have to consider, G was 10. I will write 50 was 3 by 2 times N1. That is giving me N1 equals 100 over 3 newtons. And from the above equation, I will realize that N2 would be 50 minus 100 over 3, that is 3 by 3 newtons. Going to be my answer. Okay, N1 is 100 by 3 newtons and N2 is 50 by 3 newtons. So I hope these were the answers that you guys had also gotten. And I hope now you know how to approach these problems of equilibrium. Okay. First, draw the FBD. Second, write the expression for translatory equilibrium. Second, write the expression for rotatory equilibrium about any point that you feel like. Okay. All right. Why don't we give one more problem a try? So here you've been told a rod AB rests with the end A on a rough ground and the end B against a smooth vertical wall, and the weight of the rod is W. If the rod is making an angle of 30 degrees to the horizontal, find the frictional force on the end A and the normal reactions on both the ends of the rod. So let's see how the situation is first of all. So it is something like this. So you have a smooth vertical wall. Yeah, smooth vertical wall. So here you have mu is 0, and then you have a rough horizontal surface. So there is some new here. Okay, yeah, rough ground. And you have a rod AB which is resting with its end B against the smooth vertical wall. Okay, so let's draw ourselves that rod. This imagine is the rod. Okay, so that is end B. This end B of the rod. End B is resting against the smooth wall. End A is placed on this ground, and it makes the rod makes an angle of 30 degree with the horizontal. So if it makes the angle 30 degree with the horizontal, let's mark that also for our reference. So this angle would be 30 degrees. Okay, I hope you got that. Now you will realize what all forces will be acting from the wall. You would have some normal reaction. Okay, I am going to help you with that now. Okay, so let's try and draw the FPD. So you would have had one N. Let's call that N1, which will be in this direction, acting on this rod. You would have had another N2 acting like this. Now you will realize you will also have an mg, so the weight, and then you would have had friction coming from the ground. In which direction? Can you guess? See, for translatory equilibrium, somebody has to balance this end, right? This end has to balance somebody. Who is the only force who can that can come in the x direction? That is the force of friction. So you would have had a static friction acting in this direction. Okay, so these are the forces that will be acting on the rod. Two normal reactions, one friction and one weight W. Okay. Now you have three unknowns, N1, N2, and F. And how many equations do you have? So you will get two equations from translatory equilibrium. Why? One for x equilibrium, for equilibrium in the x direction, another for equilibrium in the y direction. Okay, so two summation f equals 0 equations. One you will get for rotatory equilibrium. So you will have yourselves three equations and three unknowns. Okay. So let's hope you guys got this and you guys have solved this. Yeah. I'm going to wait for 1 more minute for you to solve this. And though yes, this is a recorded lecture, and though I am not able to read your chat and tell you whether you have done it correctly or not, but I would still like you guys to try. When I tell you to try a problem, you should always try it. Whether you watch it a recorded, you watch it a recorded lecture later also, or you are watching it live also. Okay, so this is meant for your own practice, for your understanding. So try this, and let's see if you can answer these questions. So this is to help you build the problem solving brain. Okay, so when you try all these questions, if you do something wrong, if you follow what I try to do and how I approach any solution to a problem, that is how you will also develop your problem solving acumen. I hope you are trying. And yes, we have almost completed 1 minute. So I hope you have got your answers. Okay. So let's try and solve this now. Okay, I think that's enough time for you guys. I had already given you help with the FPD. Okay, so what I can say is that first I will start always by always making the FPD, which I already made here. Then second thing that I'll always do is always write the translatory equilibrium equations. So can I say that for translatory equilibrium, I will have two equations. One, look at the vertical forces. So in vertical direction, I have mg and n2. Can I say mg must be equal to n2? That is my first equation. Second equation, I will realize that the force of friction must be balancing n1. So second, I will write F equals n1. Now, please note, I will not write f as mu n1 or mu n2. Why? Because this is static friction. Mu n2 is limiting friction. Static friction can be less than limiting friction also. So do not, in case mu was given to you, do not write mu mg as f. Okay, and conclude that n1 from the wall would be mu mg. No, do not make that mistake. That may or may not be the case, by the way. And these are the small things which you need to be careful about. Okay, F is static friction, which only needs to be less than equal to mg. Okay, N2 I already found was mg. Okay, or in other words, W was given to me, right? So W I already know N2 as. Okay, all I need to calculate now is either F or N1 because both are equal. So now, which point to take the torques about? Again, you have an entire range of choices. So you had A, you had B, you even had C, which let's say is the center of the rod where the weight is acting. Okay. Uh, however, I just like choosing the point A. The reason why I like choosing point A here is that that leaves me with torques of minimum amount of force. Okay. The good part about A is that two forces are passing through A. If any force is passing through any point, then the torque about that point of that force is always zero. So choosing A as my point about which I want to calculate the torques has a distinct advantage that the torques about A due to two forces is already zero. So I don't need to calculate that. So I always like to minimize my calculations. So that is why I will choose point A. You are free to choose any point as long as you write the equations correctly, you will get the right answer. Okay, so let's write for rotatory equilibrium. For rotatory equilibrium, taking torques about A. Let's see what that will give us. So I will have a torque by mg. Again, what is the perpendicular distance? So remember this trick to quickly write your torques. Okay, always go for the perpendicular distance. Okay, let's use this color. The perpendicular distance would be this. Okay, and this would be L by 2. This would be L by 2 cos 30. Okay, I hope you guys can see that. And this perpendicular distance would be L by 2 cos of 30. How about the perpendicular distance of A with from N1? Fine. This also, this is it. This would be L times, this entire thing was L times sine 30. Great. I hope everybody followed this. And you will realize one guy is trying to rotate the rod in the anti-clockwise direction. And that is mg. Mg is trying to rotate this rod in the anti-clockwise direction about A. Okay, and N1 is trying to uh, rotate the rod in the clockwise direction. So please remember, any clockwise torque is always minus k cap, and any clockwise uh, anti-clockwise torque is always plus k cap. So in case you need plus or minus k cap also. Otherwise, we just write plus and minus. That's about it. I will take the torque of mg as plus, then the torque of n1 will become minus. Okay, so let's just write those down. So torque of mg would be plus mg into L by 2 cos of 30, right? L by 2 cos of 30 and minus n1 times L sine 30. That will be the torque of n1. I hope everybody can see that. And this is 0, right? So this and this is going to go. And what I get is n1 equals mg over 2 tan 30. Tan 30 is 1 by root 3. So this is what I'm getting, root 3 by 2 mg. That is n1. Once I know n1, then I substitute this here and I will also get f is also equal to root 3 by 2 mg. Realize which could have been less than mu mg. Okay. And once, okay, so Yeah, N2 I already knew. 2 was already mg. So here are all my three answers. So N2 I found, F I found, N1 I. Okay. I hope these were the answers that you had got. And if not, go through the solution, see where you went wrong, and make sure you do not repeat that mistake ever again. Okay, making mistakes is not a problem. You will make mistakes when you're doing it for the first time. The important bit is about identifying your mistakes and not repeating them again. Okay. So with that, I hope this is clear. So should we move on? I know I can't hear you, but I still have the habit of asking. Okay. I will move on. All right. Now, I already told you that in pure rotation, if I talk about pure rotation, then I already told you this result, that summation tau external is equal to dl over dt. This is valid for all kinds of cases, for rigid, non-rigid bodies, for pure rotation, for general motion, for translation, anything. Okay, for translation, everything would be zero, equal to zero. Now, for pure translation, so pure rotation, I know that uh, L about AOR is axis of rotation. That's it. Nothing. In case you're getting confused, AOR is just the short form that I use for axis of rotation. Okay. So you already know that torque about angular momentum about axis of rotation is I about axis of rotation times omega, right? So what I can also say is you can use this equation and I can say summation of all the torques about the axis of rotation will be dl by dt, okay, which becomes I about AOR times alpha. So remember, this is the equation that you're going to use for your pure rotation. Okay, so for pure rotation and pure rotation only, general equation is tau equals I alpha. For pure rotation, it takes the form of summation tau about axis of rotation is equal to I about axis of rotation times alpha. Okay, very, very important result. This is what you will use to analyze the dynamics of pure rotation. Okay, please remember that both the uh, since you take the I about axis of rotation, so obviously you're calculating the angular momentum about axis of rotation. You also need to consider your torques also about the axis of rotation. If you're taking torques about some other point, then do not blindly use this equation or do not even use tau equals I alpha. Okay, then you use this, and you need to be very careful while using this. Okay, why? Because the formula for L will change. If you're taking thoughts about some random axis, then the formula of L you would have had to use. Uh, you would have had to use that formula. L of system of particles about P is uh, the angular momentum of Cm with respect to P plus angular momentum of Cm with respect to the Cm itself. Okay. So for pure rotation only, you can use this equation. Please remember this. Very important. We use this a lot, but it is valid only for pure rotation. Okay, how about we go about this? So the moment of inertia of a body about a fixed axis is given to you, which is 2.5 kg meter square. You have to calculate the torque, which can produce an angular acceleration of 18 radian per second square. Angular acceleration. So to produce this kind of alpha, what is the torque that will be required? Okay. So this is very straightforward. This is direct formula based. So I'm going to give you 30 seconds for this one. Okay. Hurry up and give me a quick answer. All you need to do is you know the I, you know the alpha, you have been asked the torque. So very simple, very straightforward problem. Just to get you some practice and just to get you the idea of calculating the torques and relating them with alphas. Okay. Okay. 30 seconds are up, and I am sure by now you all have your answers. All I need to you do is use this equation I alpha. Now I is 2.5, alpha is 18. So you will realize this that this is 5 into 9, that is 45. 5 Newton meter. That is the answer. That's it. One line answer. Okay, let's try one more problem. Shall we? So here you've been told a flywheel of moment of inertia 10 to the power 7 gram centimeter square is rotating at a speed of 120 rpm. You have to find the braking torque. So you are applying a torque which is trying to slow this flywheel down. You have to find the braking torque required to stop the wheel in a 5 rotation. Okay. Now pay attention to the units here. Units are all jumbled up. Okay. So make sure you're getting your units consistent, and I'll give you 1 minute to solve this. Okay. All right. So you guys try this. Till then, let me have some more water. So very, very simple problem. Again, some information has been given to you about the rotation. Why is that given to you? Initial omega is given to you. It has to come to stop has been given to you. The amount of rotations it would take to stop has been given to you. So use that all this information to find the alpha. So if you can find the alpha, then you can find the torque. You already have the I. All you need to find the torque is alpha mod. Calculate the alpha using the information given here and find the torque. Okay. Okay. Yes. So I think that concludes 1 minute, and I think by now you should have done your answers. Just be careful about the units. That's the only thing where you can go wrong. Okay. So initial omega. Let's write that. Omega initial was 120 rpm. So let's just convert this into radians per second. That'll be 120 into in one round it will cover 2 pi angle, and this is per minute. Okay, so per second it would be by 60. So omega initial is 4 pi seconds per second. What is the omega final? Final omega is obviously 0 because this has to come to rest. Now, what is the theta? Theta is 5 rotations, so that is 10 pi. 5 into 2 pi, that is 10 pi. Now all I need to do is use the equation omega final square minus omega initial square equals to alpha theta. Okay, when I do that, what will I get? I will get minus 16 pi square equals 2 times alpha into 10 pi. This cancelled, this gets cancelled. Okay. So alpha I am getting as 0.8 pi with a minus sign, which is telling me that this is a retardation, a retarding angular acceleration, radian per second square. Yep. Now that I know alpha in radian per second square, all I need to do is find my moment of inertia in SI units. So let's convert this into SI units. So this is 10 to the power 7 gram over centimeter square. So how much is 1 gram? 1 gram can be written as 10 to the power 7 into 10 to the power of minus 3 kgs over 10 to the power of minus 2 into square. Oh, this is in multiplication. Gram into centimeter square. Gram centimeter square. Here this into 10 to the power of minus. That is nothing but 1 kg meter square. That is it. Now you know the conversion also. Okay. So 1 kg meter square is 10 to the power 7 CGS units. So therefore, the torque, braking torque would be 1 into this. Or I'm only writing the magnitude, 0.8 pi Newton meter. That is my answer. Okay, I hope all you guys got this answer only, and if you did not, then go through the solution, try and identify your mistake, and again, never ever repeat that again. All right, so that is it about this question. I hope everybody followed the solution. All right, moving forward, you have another tool at your disposal, which is called conservation of angular momentum. So all you need to do is, for dynamics of pure rotation, you need to remember everything that you used to apply in translation. So what were the tools that you used to apply in translation? Let's talk about this. So first you had NLM. So let's draw a comparison, and that will help you analyze pure rotation very very easily. Okay, so yeah. So on one side I will have translatory motion, and one side I have pure rotation. So here I am drawing about translation, and here pure rotation. So the first thing that you had here was F equals ma equations. Summation F equals ma. Right. This is the equation that you had for analysis of translation. Right. Now you can use the parallel of this here. Let's have a parallel of this here, and the parallel would be summation tau equals I alpha equation. Now please remember tau and I have to be on the same axis. Okay. Similarly, what was the second tool that you would have had? So this is the first tool. Second tool you would have had work energy methods. Right? We will talk about work energy methods also in the analysis of work energy theorem. So that was one thing, work energy theorem and energy conservation. Now you have the exact same tools here. Conservation. You have exactly those tools here. We will discuss about those also. So you have same tools here. You can apply work energy theorem here also, and you can apply energy conservation here also. Again, we will take a closer look on that, don't worry. Next, you had linear momentum conservation. Okay, conservation of linear momentum. And on a parallel, here you have conservation of angular momentum. All you need to do is just remember that just like translation, you have the same three tools here. One, tau equals I alpha equation. Second, conservation of angular momentum. And third, you have energy conservation or work energy theorem. Okay, so we have already looked at this. Tau equals I alpha. Now we are looking at conservation of angular momentum, and then we will also talk about the work energy methods. Okay, so how about the angular momentum conservation? So if the net torque acting at a body or a system is zero, then the total angular momentum remains conserved. This is what angular momentum is. This is very, very similar to your linear momentum. If the total external force was zero, then the linear momentum would remain constant. Same is here. However, please note one thing is different. That if you have the net torque acting about one point as a zero, then about that point the moment of inertia or the angular momentum would remain conserved. Similarly, if about one axis the torque was zero, then about that axis the angular momentum would remain conserved. So that is a slight difference here. So is zero. So let's just add a little bit here. When the net torque, net acting torque on a body is zero, net acting torque on a body or a system about a given point or axis is zero, then the total angular momentum about that point at about that point or axis remains conserved. Okay, so please remember that it is not necessary that if the conservation of angular momentum is holding about one point, then the angular momentum would be conserved about every point. No, that is not the case. Here, this is a very, very specific scenario. Okay, if we talk about one particular point is zero or about one particular axis is zero, then the angular momentum about that particular point or about that axis is only conserved. This is a very important distinction. Okay, that is what makes the approach of conservation of angular momentum tougher. Okay, because often you don't pay attention to that. Okay, so now you will make sure that you always remember this. So you see here I have used the subscripts. So if tau about p is 0, then L about p is constant. Where tau about p may be the torque about p or about an axis passing through p. Okay? And angular momentum would also be the same. It will be either the angular momentum about the point p or about the axis passing through p. Okay? Now, for pure rotation, angular momentum about any axis was I about that axis times omega. So for pure rotation, again, the special case of angular momentum conservation becomes I1 omega 1 equals I2 omega 2. So again, remember that this is only a special case for pure rotation. Do not blindly apply this everywhere. Okay, this is only for pure rotation. That I1 omega 1 equals I2 omega 2. That is the form that the conservation of angular momentum takes. Like there you had M1 V1 equals M2 V2. Similarly, here you have I1 omega 1 equals I2 omega 2. Okay. All right. So I hope everybody followed the discussion so far. Should we go ahead and solve some problems? Again, if there is anything about today's discussion that you did not follow, then you can leave that in the comment section or remember to join me in the next live class, which would be day after tomorrow. Okay, so this is the last recorded session. Day after tomorrow, I will host a live class, so there you can ask me your doubts. Okay, or you can leave your doubts in the comment section, and I will try and answer them right there. Okay. All right, let's get ourselves some practice then. Let's see what we have learned. Can we apply that? So you've been told a mass of 2 kg is rotating on a circular path of radius 0.8 meters with an angular velocity of 44 radian per second with the help of a string tied at the center of the circular path. If the string suddenly elongates up to a length of 1 meter, find the value of the changed angular velocity. What is essentially happening is that imagine I had a string in my hand and I was rotating this thing with a constant angular velocity. And suddenly I let the string slip. If I let the string slip, if it becomes longer, you will realize that this rotating thing will become slower. Okay, so I've already given you the hint. How slow? Find it out using conservation of angular momentum. About which point? Again, always think about this. Whenever you have to apply conservation of angular momentum, first of all, you have to choose the point about which angular momentum will remain conserved. So always remember that without choosing that point correctly, you cannot apply angular momentum conservation. It will not be conserved about every point. There will be a very specific point about which you can apply the angular momentum conservation. Okay. So let's give you 30 minutes to 30 seconds to solve this. Okay, I think with all the hints. So you do that unconsciously, by the way. You a lot of you might have solved a lot of problems and applied angular momentum conservation without realizing that you were doing it about certain points only. And if you tried doing it about other points, you would have gotten wrong answers. Don't worry, don't worry. In one of my live sessions, I will take up some examples where I will show you that how you could have gone wrong if you did not pick up your point about which you are applying the angular momentum conservation correctly. This one is super easy in any case. So you guys should have already answered this. Okay. So yeah, I think more than 30 seconds have passed now. I'll go ahead and show you the solution. So what have you been told? A mass of 2 kg is rotating in a circular path of radius 0.8. So let's say draw ourselves. Okay, let's draw ourselves that situation. Imagine that this is a string, and here was a particle, and this particle was rotating with an angular velocity of 44 radian per second. This circle. Okay. Now, what you will realize is that if suddenly I let go of the string and the string is allowed to get stretched, say by 1 meter, what string becomes light, and now your particle will move in a circle of a higher radius, right? It will start to move in this radius. Now all I need to do is find the omega. How much is the omega with which it is moving now? So let's call this omega dash, and let's call the original omega as omega 1 or just omega naught. Okay, and initially let's say the radius was zero point 0.8 meters. Finally, the radius would be 1.8 meters. Now, what you will realize is that during the entire motion, what are the forces that are acting on my particle? There is only one force. What is that force? That is the force of tension. Is the force of tension. And this force of tension has a very special quality that it can never produce any torque about this point O. Okay, so you guys have must have solved this also, but you often don't realize that you can only apply the conservation of angular momentum about that point O. Why? Because only about that point O can the tension never produce any torque. Okay, so that is the entire logic of applying angular momentum conservation. So I can write since there is no external torque. Okay, so this entire setup is in a horizontal plane, by the way, not in a vertical plane. So that is why we are ignoring mg. Okay, in case you're wondering, there is no external torque. So there is no external torque on what was it? Mass. Okay, so let's consider that point mass. External torque on the point mass about O. We can apply conservation of angular momentum about it. Now my job is super easy. So what all I need to do is I need to write I1 about O omega equal to omega naught should be equal to I2 about O omega dash. That's about it. Okay, now I hope you realize that I have this habit of writing everything for solving. So this comes from the fact that I had taken the subjective JEE. So I have this habit. Whenever I have to solve a problem, I have to write the explanation of why I'm writing the uh, expressions. So trust me, try and solve everything in a subjective manner that helps you develop a logic. When you have to write the reason of everything, right? So that was why the concepts of everybody that took a subjective JEE were very strong. You do not just use the formula there while solving your problem. So you have to tell the logic also why you're using this formula, because otherwise you won't get certain marks. If you just write using angular momentum conservation, why are you using angular momentum conservation? Half a mark lost. Okay, so that is what strengthens your concepts. Okay, so now it is nothing. I1O would have been mr m into zero point 0.8 whole square to omega 1, which was 44. This would be equal to m times 1.8 whole square into omega dash. That's about it. So let's see what I am getting my omega dash as. So this is 8 over 18. 8 over 18 is Hmm. 2 by 9. Hmm. 2 by 9 whole square into 44. So let me just use my calculator. It will be way easier with the calculator. 0.8 equals 44 to 0.4 whole square. So 8.5. 8.5 reading per second. That is what. Okay, I hope this was the answer that you also got. Again, if not so, go through the solution. Try and find out where you went wrong. Okay. All right. One last problem, I guess, for the day. I think, yes, we have utilized our time very well. So why don't I give you this problem as the homework problem, and you can leave the answer for this in the comment section. Okay. Consider this to be your homework problem. You've been told a horizontal disk is rotating with an angular velocity of 180 rpm about a vertical axis passing through its center. A small piece of wax of mass 10 gram falls on the disk and sticks to it at a distance of 10 centimeter from its center. The angular velocity is reduced to 150 rpm. You have to find the moment of inertia of the disk. Okay. Another interesting situation, nice problem, and this is your homework problem. Leave answers in the comment section. Okay, all right. Yes, that is it. Okay, one last thing. The only reason why I wrapped up the problem quickly was I wanted to tell you one more interesting bit. One very interesting bit I wanted to tell you. I did not tell you. So here, in our special case, I told you that this is how you can write. This is how you can write the total angular momentum of any body, right? Of a rigid body. Total angular momentum of a rigid body is written as angular momentum of the CM itself plus the angular momentum in the reference frame of the CM. Now you will realize that this term is dependent on what point you choose. However, this term is independent. It is a property of the system. This term turns out is called something that you know as spin angular momentum. I hope you've heard of spin angular momentum when you talk about electrons. All electrons are spinning on their axes. So, and that is why, due to that spin, they have a spin angular momentum. Spin angular momentum is an intrinsic property of a rigid body. It is independent of the point of observation. It measures the amount of rotation that a body has about its own CM. Okay. That is one quick thing that I wanted to bring to your attention. This is called spin angular. And spin angular momentum is obviously independent of the point of consideration, about which point you are measuring the angular momentum of the body. This is an intrinsic property of. Okay. So that is it. That is it. That is one bit that I just remembered and I thought I'll just mention it. Again, not very necessary. Not very necessary as far as your JEE is concerned. Yes, you may blame me that sir keeps on giving useless information, but I don't know. I don't know. I always love knowing things about physics that I study. So I am a very curious guy. So I'm just sharing it in case you are interested in knowing interesting things about physics or about the topics that you read or study. Okay. So that is it for today from my side, guys. This is where I will wrap it up for today. And obviously from tomorrow I will see you live. And next time we can interact and I can see better how you feel about all the horrible derivations that I've shown you. Anyhow, so before I wrap it up for today, let me tell you that you need to get yourselves, you should be getting yourselves the Unacademy subscriptions if you haven't gotten them already. And this is how you get it. Go to the plus section of the app, select your goal as IIT JEE and click on the get subscription button. So when you are further redirected to the payment page, you can use this code RD Live to earn 10% off on all your subscriptions. Okay. You can get yourselves these subscriptions to enroll in these courses which are already going on the Unacademy Plus, and these are being taken by the JEE English team. So if you like the JEE English team, if you would like to enroll in our courses, these are the few courses that you can join. Okay, so these are three courses for 2022 aspirants or class 11 topics. Then you have four more top courses which are for 2021 aspirants or mostly for class 12 topics. Anybody can join them, of course. That is not an issue. Further, if you like today's video, then don't forget to press that like button. And again, as I keep saying, in case you can't afford the Unacademy subscription, so one, the Unacademy subscription will provide you a lot of benefits. It will provide you definitely with a clear edge in an exam which is as competitive as the JEE. In such a competitive exam, you need every edge that you can manage. However, in case you can't afford it, in case you think, okay, I don't know if I can manage it, and is there some way I can manage it without getting the subscription? Yes, there is. Follow us on the JEE English channel of YouTube, and make sure that everybody else also gets to do this. So share it with almost all your friends. Share it with as many people as you can, so that more and more students can benefit from this quality free content that is being provided by Unacademy to you guys. All right. Don't forget to press the like button and share it with as many people as you can. And also don't forget to press the bell icon to receive notifications of all the lectures in future. Now the PDF of all the slides used in today's lecture will be available for download very, very soon. Okay. Now let me remind you one last time that again this is how you should be. You should also be being a part of the Unacademy combat. Okay, so this will be a lot of fun. Plus, you can obviously win a lot of rewards and prizes. Go enroll in this quiz, have some fun, use the code RDLive and win yourself some prizes. All right. Again, those of you following us on the JEE English channel of YouTube can connect with us on the Telegram app using this link. Finally, one last time before I take your leave, my code is RDLive. So if you like my lectures, if you'd like to enroll in my courses, and if you like knowing interesting information about your subject, if you like going through those painful derivations like I do, then yes, you can enroll in my courses, and you can use my code to get your next Unacademy subscriptions and get a 10% off. So with that, I'll take your leave. You guys keep studying, keep practicing hard, and take care. Bye bye.